so this is hour 2. We're going to start talking about just wave equations and solutions to this equation in general. Waves, traveling waves, whether they be on strings or water or sound waves. Okay. And what we're going to do is we're going to use Wolfram Alpha to basically plot each of these things so I can show you why it's a wave. Okay. So here's what we're going to do. We're going to plot that function that I gave you there, which is x minus 3 times t. Now, in order to make it so that I'm multiplying by different values, and I can plot this in 1 dimension instead of 2, I'm going to say x minus 3 times 1 for 1 second. And then we're going to evaluate this to the negative 2 power, right? Put parentheses around this just in case. And we're basically going to iterate the time. So we're going to plot that function. And then we're going to plot another function where we're going to change the t in the function to a 2. Now what I'm doing is I'm plotting this function down here, right? 1 over x minus 3t, right? So 3 is 3 times 1, 3 times 2. And let's do 3 times 0 as well. So we'll again copy this. And in front of this one, we'll plot times 0. So we're gonna look at the wave at time equal to 0, time equal to 1, and time equal to 2. And we're going to look at the way that it's shaped, okay? I want to plot that between x from, I don't know what we'll need, x from 0 to 10 maybe? Something like that. And then that should do it, I think. Oh, I can't remember if I need to put this whole set in brackets, but let's see what it does. Let's see if it figures out what I'm trying to do here. Yep, so it's 1 over x minus 3 times 0, 1 over x minus from 0 to 10. And we need to increase the... I want to zoom out on my graph. I can't remember how to change the y-coordinate. How it's in large. Yeah, it's going to have some limitations on this, isn't it? Well, there's your wave. The wave is basically right here. The pulse. Here, let's expand this so we can see the left-hand side of this. What if we go from negative 10 to 10? Will it naturally just expand my y-axis up? Kind of. How do you do the y? Oh no, that's probably not what I wanted to do. It's gonna, no, I kept it. Let's see how I changed the... Do any of you guys know how I changed the y range? Oh, that's how you do it. Okay, just y equals. So I'll do the end of this. We need to have y go, comma, y, comma, 0 to what? Probably like 5 should be enough, I think. Let's try that. It's getting better. At some point, these things are going to turn over, so we go from 0 to 10. I guess I could just calculate the maximum value of the function. Is it infinite because of the... Maybe it's infinite, yeah? Because if you put x equal to 0 here, or x equal to, like this one, x equal to 0, you get infinity. Okay, so it's an infinite spike, but whatever. Okay, right. I'm being silly. There's no far... Okay, but this is our pulse, basically. Our pulse at time equal to 0, our pulse at time equal to 1, and our pulse at time equal to 3, or 2. So 0, 1, and 2, right? It's moving to the right, right? Our pulse is literally moving to the right. That's what that equation works. That's how that equation works right there. Okay? Does that make sense? Traveling wave. Shift, sliding along this, just like a pulse on a string, or a water wave. All right? If you take this function right here, you take the derivative twice with respect to x, you take the derivative twice with respect to t, you'll prove that this is true. And I'll leave that for you guys to do yourselves. I think that's one of your homework problems, actually. It's not really a problem so much as something you just do on your own to prove if something like this automatically satisfies this wave equation. Okay? So what that function is going to look like now, if we're talking specifically about the electric and magnetic fields, sorry, I dropped my pen, is that our electric fields, and I would say that we could have done this exact same derivation we just did right here, except we replaced the electric field with the magnetic fields, and we could have gotten basically exactly the same equation, just so you guys know. Del 2 T Pz. And what we can do is we can say that some of the solutions of these would be what we call sinusoidal electromagnetic waves. And what they would look like is that you'd have some form where the solution to this wave equation would look something like this. So the electric field as a function of x and t is going to be equal to some max quantity of the electric field, E max. And then you have in here some cosine, and usually the way this is written is like this, kx minus omega t. Having a similar but not exactly the same form as this one right here. And the way this also could be written is we could actually say, since it's the y component, this is really the electric field as long as I multiply it by j hat. And then I can actually remove the y component down here. This gives you the y component of the electric field, right? The part that's multiplied by j hat. And then this entire thing here, that's the part that satisfies the wave equation. That's what EY is. The y component of the electric field is given by that expression right there. Do the same thing with the magnetic field, except for the magnetic field, it's the z component, right? So it's the z component. So you would say for our magnetic field, we're going to have B as a function of x and t is going to be equal to some k hat multiplied by B max multiplied by the, also, they have to be in phase in this case, cosine of kx minus omega t. And within these definitions right here, omega is basically the kind of angular frequency of the wave, which means it's equal to 2 pi times the frequency. K is called the wave number. So this is the frequency. Specifically, this represents the angular frequency. The omega does. And then F is just the regular frequency. And then K is what's called the wave number. Oops. The wave number. And it's related to the wavelength of the wave. Okay? The wave number is K. And I believe this is equal to 2 pi divided by lambda, where lambda is the wavelength of the wave. Wavelength. And to get the speed, there's two different ways you can do it. The speed of the wave is equal to the frequency, okay, multiplied by the wavelength, or the speed of the wave is equal to it's omega divided by k. Either one of these will give you the speed of the wave. You either take the frequency of the wave and you multiply by the wavelength, or you take the wave number and you divide by k. And I hope you guys understand what I mean by this. If this was our wave, right, where this represents the y component of the electric field, and this right here represents the spatial dimension x, then the wavelength of the wave is basically the length from here to here for one oscillation. And the oscillation basically continues. Right? So the wavelength, and I shouldn't draw it like that because then the wave is like getting smaller wavelengths. So the distance from basically there to there is what we call the wavelength. And then k is just kind of the inverse of that, what we call the wave number. All right? But this is a pretty handy equation right here. And specifically, in the case of what we're talking about here, this happens to be exactly equal to, both of these things happen to be exactly equal to the speed of light c. Right? So this is equal to c and this is equal to c. Both of these are for the velocity. Okay. All right. Do you guys have any questions about that? Those end up being our equations that represent electric and magnetic fields. else do I want to say? I want to show you the other thing here, which is that there's also a relationship between the electric field maximum and the magnetic field maximum, which is that if I take the ratio, can I prove it to you from this? If I take the ratio of the electric field maximum divided by the magnetic field maximum, this ends up being equal to the speed of light also. This ratio of E over B, and also really at any given time, if I take the value of the electric field divided by the value of the magnetic field, this is also equal to C. So if you know one of them, you can find the other one. How do I prove that? If there was a way I could prove that to you guys. To look through my notes. Maybe we just state it here as something we know about the relationship. I feel like it comes from these equations, though. Okay, I'm not going to worry about that for now, but this is something we know right here. Okay, I've got a problem that we can do here. Just to get an understanding of how we can use the two equations that I wrote down, I'm going to type it out. This is kind of a long-winded one. I'm going to mute my mic while I'm typing it. You can kind of read as I write it. I guess that's the only thing. We're going to do a couple things here, but so we have so a CO2 laser emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. So what does that look like? Let's scroll down here a little bit. So let's get our axes going. So our wave is sinusoidal. So basically it's going kind of like this. Right? Oh my god, it looks so bad. A little better. We've got a sinusoidal wave, and it has kind of two pieces to it. Oh, I actually need the third dimension here. Let's just take a line and draw it this way. So there's our third dimension. And it says that if I label my axes here, so like if this is x, this is y, and this is z, then it's saying the electric field is perpendicular to the z-axis. So perpendicular to the z-axis would be basically, in my picture here, I guess, like this. This is our electric field. Okay, it oscillates up and down like this. That's perpendicular to z, right? It's also perpendicular to the axis here. And then our magnetic field, we can figure out something about, because it says that the wave is traveling in the negative x direction, so the wave is traveling back this way. That's the velocity that direction, okay? So I guess the question would be, what direction does the magnetic field point in this picture? If my electric field oscillates up and down like this, and the wave has to propagate like this, and I tell you that the direction of propagation, I said earlier, has to be the E cross B direction. They have to be at right angles to each other, and it has to be the E cross B direction. So if I want the wave to travel to the left, let's say that I come to this point right here, what direction should the magnetic field be at this point? Should it be pointing this way, or should it be pointing that way? Which one is it? If I want to make sure that E cross B gives me the wave traveling to the left. Which way does it go? Does the magnetic field at this point this way, along the z-axis, or does it point this way? Direction of propagation. Sorry, propagation. That's the word I'm looking for there. Use your right hand. If you do E cross B with this vector, you do E cross B with the vector that points in. Now these are parallel to the z-axis now. Which one's it going to be? Does B go that way, or does it go this way? Can you guys see it? I know it's hard to see this. So if that's your hand, so that this is the top of your hand, right? So that your hair, like this is like the hairs of your hand. On the other side is your palm, right? If I put my palm this way, so in the direction of E, that E is this way, right? If B is this way, if I do E cross B, my thumb points to the left, right? So that's where you get the, it has to be the one that points that way. And that tells you kind of like where the magnetic field is. You'll need to delete all these guys. So that's the direction of the magnetic field, this way. But then when it's here, the magnetic field has to point this way. And when it's over here, again, the magnetic field points that way. And here again, it points this way. So now you can see how the magnetic field's oscillating. This is where this picture is going to get really bad, but I'll do my best. This one's oscillating in the other direction. God, it looks awful, doesn't it? I'm not even gonna... That's just terrible. It's this is what I'm trying to draw here. This thing. So that's how they're oriented. And now we want to write the electric and magnetic fields as a function of time if we know the following information. We know that the wavelength, lambda, is equal to 10.6 micrometers, so that's 10.6 times 10 to the negative 6. That the maximum value of the electric field, E max, is equal to 1.5 million, so 1.5 times 10 to the 6th volts per meter. And what else do we know? That's all we know. We have to kind of solve for the other information. So let's first of all talk about the electric field as a function of time. So what we know now is that the electric fields, if we look at our equation that's just like a little bit above here, we're going to take the value of the electric field, okay? It points in the... Oh my god, I messed these up again. This is not X. What is wrong with me? Cut, paste, move. This is X and Y. Cut, paste. There we go. I would say that my electric field's oscillating up and down in the j-hat direction, and that the value of the electric field is 1.5 times 10 to the 6th, the max value. And then we're going to use a cosine function for this. It can be a cosine or a sine, really. It's a traveling wave. And we need for this the k, which is the wave number, multiplied by x, minus omega t. Except that our wave needs to travel to the left, so we're going to make this a plus sign, I think. Because otherwise it won't travel to the left. Right? Think about that for a second. Yeah, if it travels to the left, this thing has to be positive. Has to be positive. And this is where I can go back to this picture to show you that. So this was a wave that was traveling to the right, right? This was t equal to 0, t equal to 1, t equal to 2, right? I believe if we change these to plus signs, just to show you, this one doesn't matter actually. Plus and plus, I think it will move backwards now. Oops. Just like when you shift functions. Yeah, now it starts t equal to 0, t equal to, so it's moving left now, right? So I think we have to do that in this case. Now what's k? Well, k is related to lambda, right? So let's calculate what that is. So k I said was equal to, if I take 2 pi and I divide by the wavelength, so that's going to be 2 pi divided by that. We can calculate very quickly what that is. So it's basically, so 2 times pi divided by so 592, so it's basically 5.9 times 10 to the 5, right? Yeah. 5.92 times 10 to the 5. And the units for k are basically meter negative 1, inverse meters, because lambda is measured in meters. We also need to know what omega is. For that, we use this relationship here, which says that the velocity of the wave, which is c, if I take that and I multiply by k, that gives me omega. That's, you can't see it because that's that equation right there. So if we take the speed of light, which is 3 times 10 to the 8, and we multiply by k, which is right there, that should give us omega. So we just take the answer that we just got, and we multiply by 3 times 10 to the 8. We'll get 1.79 times 10 to the 14. The unit for this one, oh no. The unit for this is like inverse seconds, or usually what we use is hertz. So we can put both of these numbers inside of our equation right here and get that the electric field as a function of x and t is equal to, this is like a lot of numbers to crunch in here, so it's 1.5 times 10 to the 6th volts per meter, cosine of, so k, where's k? There's k. So it's 5.92 times 10 to the 5 inverse meters. That is times x. So kx is going to give you units of 1, and then plus omega, which is this, 1.79 times 10 to the 14 hertz times t, and that is your electric field as a function of time. And the next thing we want to do is do the same thing for the magnetic field. So to do that, we use this relationship right here. We can find the value of the magnetic field, right, if we just take E over C, right? So let's do that really quickly here. B max, according to that equation, is equal to E max over C. So it's equal to this, 1.5 times 10 to the 6th volts per meter, divided by the speed of light, which is 3 times 10 to the 8. Not 18, 3 times 10 to the 8 meters over seconds. And that is going to be equal to, it's pretty easy to do actually, because 1.5 divided by 3 is 0.5, and then 6 over 8 is negative 2, so it's going to be 5 times 10 to the negative 3, I think. Just check real quick with the calculator. Yeah, 0.005 or 5 times 10 to the negative 3. So knowing what that is, then the magnetic field as a function of x and t is going to be equal to, I have to write all this stuff out again, but now it's B max, which is this, and then times exactly the same thing. So I think we can probably just copy paste this part. Yep. Box in that, copy, paste, boom. That part's the same. It's not going off the screen. But there we go. That's magnetic field as a function of x and t. There's one thing missing here, which is this piece right here. Now, this is where we got to think about our picture right here. Notice that when the electric field is positive, the magnetic field is negative. And when the electric field is positive, the magnetic field is... Wait, sorry. When E is negative, B is positive. When E is positive, B is negative. So we're going to have to throw in, first of all, a K... Ooh, that's nothing. There we go. K hat, because the magnetic field is oscillating only in the Z direction. And then a negative sign. And there are our two equations that represent the electric and magnetic fields of this wave. Right there. Do you guys have any questions? You got a couple problems like this on your homework. They're not that hard. It's really just about knowing something about the definitions, like velocity is equal to frequency times wavelength, what these things are, wave number, angular frequency, and just distinguishing between the different, language. It's really... Problems in this chapter are not particularly difficult, but yeah. Here we go. That's electromagnetic waves. This is effectively kind of the culmination, what we did today, of all of Physics 1C. While there are a few more details that we'll discuss about radiation pressure and about the energy carried by waves, we are effectively done with Physics 1C now by solving like what we've just done here. By proving that effectively using, we used Faraday's law and we used Ampere's law, basically solved them simultaneously. We got one equation here from solving, this was the Faraday law, or Ampere law. This is what we got from the other one. And we basically just pushed together these two equations into one equation, which gave us the wave equation for light. The relationship between what the electric field does and how it varies in space and time, and the relationship for the same thing for the magnetic field. We said that these are basically solutions. Solutions to these are going to be anything that has the form, something like x minus vt. Now, the normal way in which these are described, and I don't know why, but this is normally how they're written. You can get more information because you have this and this instead of just a speed. Anyway, it kind of shows that you can take two different phenomena, right? Like the big picture of what we did is this. We took electricity, the motion of charges and the field lines that they produce, and we added to that magnets, magnetism, whatever you want to call it, and you get light. That's it. Maxwell's equations tell you how these interact with each other, that when the electric field changes, it produces a magnetic field. The changing magnetic field produces an electric field, and the combination of those two things creates waves that basically just propagate through space. Light waves. And the light waves, this is... I don't know if this is meaningful to you in any way, but quite literally, when you describe a laser, one of the ways we analyze and understand the light wave of a laser is by talking about the maximum values of the electric field and the magnetic field. It's one of the properties of a laser beam, right? I don't know if that's... You might think of a laser beam, think of it like a pointer. It might have a color. Well, what's the color? The color is actually contained within these numbers, like here and here. Either one of these numbers here represents something about the color. This particular frequency is this frequency of light. It's a certain color of light, right? But light doesn't just have color. That's what I'm telling you. Light doesn't just have color. It also has electric fields and magnetic fields contained within it. And when you study optics, you study how the electric and magnetic fields interact with each other to do these things. Like, these are important quantities when you're describing the power output of a laser beam, when you're describing, So it's a really powerful idea that light is an electromagnetic wave that, yeah. So there you go. You guys have any questions? I have 1 page of notes left for the whole semester. Yeah, 1.5, I guess. So I guess that's what we'll do. Well, we have 1 more week, right? We'll either finish it next time or we'll just skip a week, or skip this week's Thursday class and then just meet again next Tuesday, since we only have 1 day left. Or maybe we just finish it up this Tuesday and you guys can have the last week off. Maybe that makes the most sense. You can have the last week off to, finish up your homework and stuff like that. I'm sure you're going to have a lot of projects and stuff coming, so maybe that's what we'll do. We'll finish by talking about energy and momentum and radiation pressure. We're going to talk next time about how what are called solar sails work, how you can basically ride on sunlight, kind of like you can ride on ocean wind. Okay, so I'm going to stop the recording there. Let me know if you guys have any questions.